Yeah, my name's Mark. We're going to take a shallow dive into Clickhouse. I just wanted to mention that this is also a picture of me rock climbing. You can't see it because it's cropped so close. I have 2 casts, 1 on each leg.
Boom.
Pretty high up, too. A few thousand kilometers. So, has anyone heard of Clickhouse? Can we get a show of hands? All right, a few people. Cool. I'm going to sound very smart. So, Clickhouse is a column-oriented DBMS, and its purpose is to run analytical queries on tons of data. This can be text or numerical data. It has the capability to scan billions of rows per second. The data is stored in columns. It's laid out on the file system by column as opposed to row. It also has a vector engine that can process those columns very efficiently. It doesn't have an indexing other than a primary composite key, which allows for very efficient seek to points of time. And you can run many concurrent queries, and they will complete in several dozen milliseconds. One of the huge benefits of using this versus something like Lucene is the ability to insert millions of rows per second. It can scale linearly, so the more servers that you add, it's going to scan that many more rows. It also has support for approximate calculations, some probabilistic data structures in there, and sampling. So when you are someone who doesn't want to pay a lot for storage, you can sample your data. So also, it's you can set up replication for high availability, and to make your queries run faster, you can set up your cluster with as many nodes as you want, and you can dispatch your queries via distributed tables to each node, and then it aggregates the result. Cool. So I'm actually going to show you a demo. Okay. So this is a setup of a few nodes in a distributed setup. The coolest thing, well, maybe not the coolest, but one of the cool things about Clickhouse is that it's SQL. So if you're very comfortable using DBMS, it's very easy to use. So let's see what kind of data we have here. So looks like we have 3 tables. Events, looks like they're tables by date. I know it looks like I don't know what's going on here, but I made these tables. I'm just pretending like I'm exploring, so just follow along. All right, so I wonder how many events we have in one of these tables. So let's just check in the first one. Home. Looks like I have 1.97 billion events, and I just want to take a moment to let you know that was a real count. It doesn't maintain a counter in memory. It was that fast. It was 40 milliseconds. Looks like I have 3 tables. Each one's a day's worth of data. How am I going to get a count of all those days? Well, it looks like I have a little handy regular expression table matcher here, so I'm just going to use that. All right. So we counted 3 days worth of data, which turned into 6.24 billion rows. That's pretty impressive. That completed in 53 milliseconds. That's pretty awesome. Have any of you tried to store that many events in like SQL Server or MySQL or something? It's kind of painful to do some of these queries on that. All right. So that's easy because like, maybe it's probably counting from the index, the primary key index. So what if we add a date predicate in there? Yeah, let's group it by date and see if we can count how many events break it out per day. There we are. So that tells you what is in each day. That completed in, how fast is that? 479 milliseconds. It's pretty awesome. Days is easy. What about if we group by hour? I'm just trying to select some text here. Yeah, let's group by hour. Yep. So what we have to do here, each one of these events, which by the way is just random text, it also has some other attributes that I added. It has a received at, and so I'm simulating like when these events were received by my imaginary server. So what we need to do is truncate that received at to the nearest hour. So we're going to choose the start of hour and group by that. All right. So here we have each hour of the day, and we've sorted this. I think I sorted it. Yeah. I sorted it by which. It's going to be hard to get my cursor over there. Yeah. Yeah, so you can see that this is the top hour, right? It's kind of hard to see there, but that processed in 581 milliseconds. So these numbers are a little hard to read. How about a histogram of a day? Okay, there we go. That's pretty cool. Now we can get a better visualization of it. I happen to know that these events have like a source ID, like I was talking about before. So I wonder how many distinct sources are in this data set. I have a feeling we're about to find out. All right. So we just did a query that ran a count distinct of an integer over 6.24 billion rows, and found out we have 10,000 unique sources. That was how long? 722 milliseconds. I think that's pretty cool. So I'd kind of like to see that previous histogram, or am I even, yeah. I want to see that bar chart again, but I only want to see it for the top 10 occurring sources. Can we do that? Do you think we can do that? Any guesses?
Yes.
Okay. While I'm trying to select this text. All right. So what we're doing here is a global in a subquery. So the subquery is going to find the top 10 occurring sources, and then we're running a global in on that. And then there we go. That is 820 milliseconds. Am I out of time? Okay. Yeah. Okay. For completeness sake, I just want to find out the lowest occurring sources. That's pretty sad. Those sources don't send very much. That was 500 milliseconds. Before we wrap up here, I've been counting integers and doing the distinct query. Of course, that's going to be fast. How about we do it on a string? So, oh, I have a typo. So there we go. So this is using unique combined. We scanned 6.24 billion rows in 3 seconds and did a distinct on a string value. How it does this so fast, it uses 3 things. This is an approximate function, but it's very accurate. The error rate is very low. It uses a hash table and a hyperlog log. Okay, we're all good. That was it.